Alright, so we have CCNA1 Chapter 5, Ethernet, which is going to be a review of our network access that we studied, which is, remember, network access is part of the TCP IP model, where it includes data link and physical. Now this one is basically at the data link, but it works with the physical layers as each layer works with each other. But Ethernet is going to be a set standard. Remember, we looked at different types of frames. We looked at 802.11, the wireless frame. Now we're going to look at Ethernet, which has to do with copper and fiber optic, right? Not long-range fiber, well, some long-range fiber optic, but not like the submarine fiber optic. What are we going to cover today? Describe the operation of the Ethernet sublayers. Identify the major fields of the Ethernet frame. Describe the purpose and characteristics of the Ethernet MAC addresses. Describe the purpose of ARP. Explain how ARP requests impact network and host performance. Explain basic switching concepts. Compare fixed configuration and modular switches. And configure layer 3 switch. This is a horrible idea. Shouldn't be happening until our chapter's over, but it is, so I guess we just have to deal with it. As you probably remember, the data link layer has two sublayers in Ethernet. That is the same. We have the LLC, which remember is doing the software drivers, and then the MAC, which is handling the physical layer, the hardware, and allowing different technologies to connect together off of the physical. So our speeds allowed are 10 meg, 100 meg, 1000 meg, 10,000 meg, 40,000 meg, or 100,000 meg, which once I hit 1,000 meg, that's also known as a gig, 10 gig, 40 gig, and 100 gig. Okay, so as you can see here, the MAC sublayer is actually has two sublayers inside of it as well, but the LLC is working with the network layer with the drivers, where the MAC is working more with the frames off the media, getting those bits into frames. So the two roles of the MAC sublayer is data encapsulation and media access. So with data encapsulation, we have frame delimiting, which is the framing process provides important delimiters that are used to identify groups of bits and make them up to a frame. This process provides synchronization between transmitting and sending nodes. Addressing the encapsulation process also provides for data link layer addressing. Each Ethernet header added in the frame contains the physical address, the MAC address that enables a frame to be delivered to a destination node. And so what that actually means is we're going to be dealing with these. We're going to hear MAC address. You're going to hear that all the time. So a MAC address is the same thing as an Ethernet address. It's just the same thing as a hardware address. If you're on a Mac computer, it's known as a hardware address. So error detection. Each Ethernet frame contains a trailer with a cyclic redundancy check, a CRC. The frame context after reception of the frame, receiving node creates a CRC to compare to the one in the frame. If these two calculations match, the frame can be trusted that it was received without error. And then we have the actual MAC sublayer of the MAC. And the second responsibility of the MAC sublayer is media access control. Media access control is responsible for the placement of frames on the media and the removal of frames from the media. As its name implies, it controls access to the media. This sublayer communicates directly with the physical layer. Alright, so Ethernet is a contention-based technology, which means everybody's sending at the same time. And so the characteristics of contention-based is stations can transmit at any time, collisions exist, and so we need mechanisms to exist to resolve contention problems. So what do we do when we have a collision? And so this has to do with Ethernet and wireless, Ethernet at half duplex and wireless at half duplex. And so CSMA stands for carrier sense multiple access, and CD is collision detection, and that's Ethernet, and collision carrier sense multiple access collision avoidance for 802.11. The difference with the CD with the wired network, what it's doing is saying hey, if there is a collision, we're going to send a random backoff timer, and everybody's going to start transmitting again until we have another collision. Where the CA says, all right, is it clear to send? All right, now I'm going to send. So everybody tries at different times. So that's the two differences, but we will be talking about that more. Okay, so now we have this MAC address, this Ethernet address, whatever you want to talk about it, and or call it. And so what the most important thing about it is the OUI, the organizational unique identifier. It tells you who makes the network card that you are using. And it's in the first 24 bits. The second 24 bits is just a randomly generated number. You know, NIC interfaces, just the identifier after the OU. And so the whole thing is 48 bits. And now remember, sometimes they ask these weird, that 8 bits make a byte. B-Y-T-E, right? And 4 bits make a nibble, and that's not a joke. That's real. It is a real identifier. So the OUI has 6 hexadecimal digits, and the identifier has 6 hex. So like 00602F, we could look at the IEEE registration website and say, hey, that's Cisco, and then Cisco would probably know what particular device this was. But that's what's nice about the Mac. We could go onto a switch, see how switch port was going, was not working correctly, and we could actually say, alright, let's identify the device, or we could have a person give us their MAC address and find out what switch port it's on, and troubleshoot whatever is going on from there. So with frame forwarding, what this MAC address actually is if we look at it in like a mail type of way, the IP address that we have talked about, or we haven't yet got to the network layer, but it would be like your home address. And so this MAC address is your actual name. It would be like me saying, Don sending to student 1, right? And so student 1 says, I am student 1, I can pick this, and hopefully your name's not student 1, but it all works out. So that's what you want to think MAC address is at. This MAC address is what's allowing you to finally receive the frames that are being sent on the network and accept them, and that's what this data link layer is doing through Ethernet. Right here, the last frame I skipped, it's pretty interesting. It's just a history of Ethernet. Feel free to take a look at that. But then they're talking about this extra 4 bytes that we have inside of our frame that we don't talk about. And I'm not going to talk about it either. It has to do, we'll talk about it in CCNA2. It has to do with VLANs, typically. But it could also do with QoS. And remember, QoS is quality of service. It's given us the ability to let traffic go before other traffic. So here's our base frame. And so we have our preamble, right? And that's our frame delimiter field where we're starting, and basically it essentially tells the first few bytes to tell the receivers to get ready to receive the new frame. Then we have the destination MAC address, so it's sending this along, and the computer that it's sending it to will say, oh yeah, that is me, and I can receive this frame. And then the source MAC address tells the computer where it was sent from. Then we have the length field, and this is an older thing. We typically call it the type field, and it usually tells us that we're using IP version 4 or IP version 6. Then we have all the data, which is the packet, which has everything in it, but that's just our encapsulated data that's going in there. And then we have our frame check sequence, which is the FCS is using the CRC to make sure there's no errors, kind of what I just read that about. And so yeah, that is our 802.11 frame, just as you saw it yesterday, or in the last chapter. Alright, so now this is an important chart. Jot this down in some way. Actually jot, well, this one down is fine. But this is decimal binary conversion, and you are going to need to learn to do this when we do subnetting, right? 0 means 000, and 0 is the same in hexadecimal. Basically, decimal, if you don't know, that's our counting system, and we count to 10, and then we start over, right? Once we get to 11, we start over. In binary, right, this is our computer's counting system. We count to 2, and then we start over. And you can look down there and see what I mean. And on hexadecimal, we actually count to 15. So it has a base of 15, whereas decimal has a base of 10. So you can convert those like so. And so one hexamal digit is actually 8 bits. And why do we care about hexamal digits? Well, IP version 6 is in them, and so are MAC addresses. So we look at this MAC address, and if we issue a command ipconfig/all, it's going to show us our IP addresses and all that. But if we look to where they've highlighted for us this physical address, or if you're on a Mac, again, it's going to say hardware address, and you're actually going to use ifconfig/all, or you can go to your Spotlight and look in your network connections and your hardware addresses in there. But if you look at those, our MAC addresses on Windows are, and I don't remember how they're written down on Macs, but they have the 2 hex digits and then a dash. And as you can see, hex digits go clear to F, so we can have letters and that kind of thing. If we're on a Cisco device, they would actually write them down in pairs of 4. We'd have 3 pairs of 4, right? And so we have 12 digits altogether, equaling 48 bits, as I've already talked about. And remember, this first half of them will tell us what vendor makes the device we are on. That's called the OUI. Alright, so now we have different kinds of traffic, and this goes for whether you're on a network or whether your network is sending unicast or sending broadcast or sending multicast. If we're doing it at a upper layer level, we can do it at a lower level as well. And so at least at layer 2 and layer 3 both have it. And so what a unicast is it means that we are sending, like, this source will send to one person at a time. And let's see what our video actually says. And how we can tell it is it has a unique MAC address here. Okay, so our broadcast and multicast are going to say different things than our unicast, right? So our unicast is a unique address, where our broadcast and our multicast are they're set in stone, or one of them, they start with something at least that makes them a unicast. So if we see completely unique address, it's a unicast. It's sending to one person. Now if we have a broadcast, we go to all Fs, so all Fs is the last digit of hexadecimal, a hexadecimal address. And so what this says is the computer will send to everyone on a network. It will broadcast this to everyone. That's a broadcast out to everyone. And so then our final is a multicast. And so our multicast is actually just converting 224 into hexadecimal. And what they do is they do 01005E. So this will be a test question. You will see, and they ask you several times, but anytime you see 01005E at the start of a MAC address, it's a multicast. So multicast means one to many. Not everyone, but to many people. More than one. And so a layer 2 multicast starts with 01005E. Store that in your head. Also store that a broadcast is the all Fs, right? So maybe that'll help you remember it. Whereas a unicast is just a unique address. Okay. So MAC addresses and IP addresses, both important, and the IP addresses get registered. And I guess so do the MAC addresses, but the MAC address is on the local network, whereas we can go down, we can say, hey, an IP address can track you back to where it's registered in this logical address, and it'd be assigned here. But why we call a MAC address a physical address is because the vendor assigns it. Whereas in a logical address, right, we can go into our network connections and hop into our adapter settings. And if I wanted to, I could set this to any IP address. It might not work, but I could do it, right? So I actually program it, not the vendor. And so it's logical. It's fake. It's not really there, but it's the logical address. Now the physical address is the burnt-in one, and that's the MAC address. And we need them both for end-to-end connectivity, right? Like I said before, our IP address is telling us, hey, go to this house. But the MAC address, and so our network is a neighborhood. And then in that neighborhood, the MAC address is telling them the name, right? And so that's what's going on. And as you can see, the in Ethernet, in all technologies, but especially what we're looking at is Ethernet, the destination and source MAC address are encapsulating the source IP and destination address. And so why it does that is these are frames that could be sent over different technologies, and then they come back after they get to their destination. They're built back into, some kind of frame. So actually every time you saw this leave, this first field, this destination MAC address and source MAC address, is changed on every hop, which means every time it goes through a router, it's going to change. And so the logical address stays the same through all networking. But we need both addresses for a network to work. And so they do a Wireshark activity. Could be interesting for you. If you don't have Wireshark, it's a wonderful tool, and we will be using it in the future. Alright, so we need both these addresses, but I'll give you an example. Switches are a layer 2 device, and PCs and routers are a layer 3 device. And so they work on IP addresses while these work on MAC addresses. So we have to have a protocol for a layer 3 address to map to a layer 2 address so it can send frames, so we can forward frames across the network. And that's called address resolution protocol. So what it's doing is it maps a layer 3 address to a layer 2 address. So it lets the computer know, hey, this IP address over here, if you want to send there, this is the MAC address, or of your default gateway, this is the MAC address. And here's the function. If we look at this, that's what it's going to show you. Maybe you can explain it better. Bam, sends it out. Who is this? I'm looking for this IP address. It says, hey, this is me, this is my MAC address. Okay, now it knows that MAC address, and it can send the information on. And why does it have to do that? Because remember, we're sending these in frames. And basically, this is just showing you how ARP works. So when a computer goes on, it's going to do an ARP broadcast. So it broadcasts to everyone, and they reply, hey, this is me, this is me. And so then the host builds an ARP cache, which gives it an IP address mapped to a MAC address, so that when its NIC gets that, we can send it out to that MAC address. Because we're actually looking on our destination, because we're layer 3 device, we're looking for, hey, if I want to go to 10.10.0.3, I'm going to send it. And so then this ARP table allows us to build a frame, because we have our source destination MAC address burnt into us, and then our source address MAC address burnt into us, and our destination we have found through ARP. So ARP only happens on layer 3 devices. And then when we go into remote communication, basically we say, hey, it's not in our network, and so we have this thing called a default gateway. And then so anything we send out of our network is actually going to be the MAC address of this interface for a default gateway, because remember, once it gets to this router is going to strip off the MAC addresses and change it to the router source address and the destination to wherever the router is sending it. But if that doesn't make sense, don't worry, we have more chapters just based on that. So we can remove ARP addresses. I don't know whether it's showing. This isn't a very common thing, but apparently Windows stores an ARP entry for 2 minutes. If you choose again, extends it for 10 minutes. Anyways, it'll be taken out of there. If you want to take out the ARP address, it either times out, or you can say, I believe it's ARP:A with like a D in it. ARP-A. This is going to show our ARP table. Is it going to show us how to delete one? I don't remember exactly how to do it. On a router, you just show IP-ARP, but on our computer, go to command prompt and say ARP-A. Feel free to take a look at that if you want to. It goes a little something like this. And you could always pull out Packet Tracer and do it on a router as well. And so it's just going to show you that mapping. And notice we have dynamic and static. And so static, you're always going to have some static, because if you notice, this is what shows us our layer 2 broadcast, which is actually the broadcast of our layer 3 as well. And those are set static. Our computer learns those statically. We could program ARP statically if we wanted an extremely secure network. I've never witnessed that in real life, but maybe the NSA or something actually is programming ARP instead of doing a ARP broadcast. And I guess another reason to do that would be you would have ARP broadcast, but basically that's what's going on is ARP can. The two problems with ARP is if your network gets too big, and you have too slow of media, it's going to lead to a lot of network traffic. And secondly, because of the broadcast, and then secondly, security. This computer could do what's called ARP spoofing and say, hey, actually I am this guy, and so that gives you a hacker technique. And that was from, like, if this computer says, hey, are you this guy, this computer would reply each time an ARP spoof and do either a man in the middle or a denial of a service attack, which you'll learn about in security, hopefully. So mitigating, we can segment them so broadcasts only go to where they want to go. Switch allows that. I'm not going to get into it very deep right now because it's for another chapter. That, or just manually setting ARP. So actually here it's going to show us this. We're going to go from this source to this destination. So remember, this is layer 2. And a switch, actually, this is why it stops ARP, is even if that was a broadcast, it would send it back, but then it would only send it to one. Where in a hub is called also a repeater, and a hub will just forward to everyone on this network. Where a switch, if it has a destination and a source, it only forwards to the destination. So it builds its MAC address table based on the source MAC, but it only forwards based on the destination. So it builds a switch MAC table, a MAC address table. So what it does is when it receives a frame, it says, hey, on port 1, I received the source MAC address of PC1, and so I'm building my table. So as soon as there's any activity and a frame comes across, the switch builds this MAC table based on the source MAC address of each PC or the device it has been received on. And what it would do if it didn't know a MAC address is, say this guy was looking for a destination and it's port 2, which is empty, the switch would forward it out every port except the one it received it on. Because if this computer is asking to get there, it knows that where it's looking for is not on this link, but it will forward it to here and to PC3. PC2 and PC3 would both receive it, just to make sure that they are not that host. And that would only happen, right, if we didn't know the source MAC address of a device that is the destination in the frame. And I'm guessing we'll be talking about that a little more. So switch is full duplex, and so it's point-to-point attached to a switch port, which means it's going to go full duplex, which means both ends send at the same time, and there's no collisions in a switched network, and so we don't have CSM CD. Whereas with the hub, remember, anything that's received on this hub, anything that's connected there, it's going to broadcast all of it out of every port, so it's very likely for collisions. Not only that, but in half duplex, you try to send, and you just say, hey, this isn't busy, but say this was forwarding out more information and was coming down, that's called a collision. And so a collision causes latency, so then we have to run the CSMA CD, which just does a random back off on all the devices, and then they all try to send again until another collision happens. And so all half duplex actually means is that you send one side at a time, right? It's like a one-way bridge, or a small narrow bridge. You can go through it one way, but if another guy is gunning it down here, there's a collision, it's a bad news. Whereas a full duplex is a two-lane bridge where you can send and receive at the same time. And so probably not going to have a collision. Auto MDIX is a switch technology that allows you to not have to build the correct cable. Typically, like devices need a crossover cable, which that wasn't a like device, but so anyhow. But so these two would have straight through, but these two switches, because they're not like devices, they would need a crossover cable. And the technology that allows you not to build the right cable is called Auto MDIX. And it is on our 2960s in the classroom and 2960Xs, but all of our 2950s, you're going to have to build the right cable through. So if you're going switch to switch, you need to build a crossover cable, which we have another section on that. Okay, so now we have switching methods. We have store and forward switching, which most of our switches are like this, and then cut through switching, which is super fast, and it's used for storage area networks, and 6509 switches can support it, and then what's called the Nexus series in Cisco, which are data center switches. And what it does is this one starts forwarding extremely fast. Store and forward receives the entire frame before it forwards it. There's two types of cut through switching, and so in cut through, it's actually going to start sending before it's received the entire frame, and it's used for where we need extremely fast networking. And so, as this is saying, you receive the frame, check the CRC, make sure it's good, and then forward it on. Whereas cut through, we have two methods, and so we have fast forward switching, and it just starts going, right? And so fast forward switching offers the lowest level of latency. Fast forward switching immediately forwards a packet after reading the destination address. Because fast forward switching starts forwarding the entire packet before the entire packet has been received, there may be times when packets are relayed with errors. This occurs infrequently, and the destination network adapter discards the faulty packet upon receipt. In fast forward mode, latency is measured from the first bit received to the first bit transmitted. Fast forward switching is the typical cut through switching method of switching. Then we have fragment free. In fragment free switching, the switch stores the first 64 bytes of the frame before forwarding. Fragment free switching can be viewed as a compromise between store and forward and switching and fast forward switching. The reason fragment free switching stores only the first 64 bytes of the frame is that most network errors and collisions occur during the first 64 bytes. Okay, so anyways, it's your happy medium, but like I said, you need a fairly expensive switch to be able to do these kind of things. Your typical switch is just storing forward. Alright, so then we have these buffering, and the reason we have buffering is, I don't want to do pink right now. So we have a switch like this, bam, and we have 24 ports on it, and it feeds to a router right here, and then that router feeds to the internet. That's the internet up there. And so these ports are all the same speed probably, and so there has to be some kind of buffering, because what if traffic's coming from here and here and here? Well, this port gets overloaded, so we need buffering to share it. So we have two types: port-based. In port-based memory buffering, frames are stored in queues that are linked to a specific incoming port and outgoing port. And then we have shared memory. Shared memory buffering deposits all frames into common memory buffer, which all ports on the switch share. And so it's just two different ways to buffer incoming traffic. Switch it. This is a great activity. Try this out. Make sure you understand how it's working. We have two types of switches, fixed and modular. And so let's talk about this right here. This is pretty cool. PoE is power over Ethernet. I think I might have talked about it with you guys already. But what it does is it allows us just to run an Ethernet cable to a phone and have it power it, or to an access point. Otherwise, we'd have to have an electrician run power to all these things. The switch actually provides power to network devices. But here we go on our switch form factor. So fixed configuration, that's what we have in the classroom mostly. That's what you're going to be seeing, and they're usually LAN design switches. And so what they do is they have a set like 24 ports. Some of the new ones, you have a set, they're still fixed configuration, but you could pull out, I don't know, redundant power supplies or redundant fans. There's still fixed configuration because you can only have 24 ports. Even though you have these modules over here for fiber, it's still fixed configuration. Now where we have these bigger modular switches like the 6509, which runs the infrastructure, and so that 09 on the 6509 means it has 9 slots for different line cards or different blades, and so you can increase port size, you can put fiber modules in, you can do whatever you want, but it just gives you they have firewalls that are built inside of them to do them. They have all kinds of things. So that's a modular configuration switch. Then stacking is, if you look at these weird cables, and we have some in the classroom, stacking is just all these switches. You plug this in, and you'd only have to put one IP address on them, and they all virtualize as one switch, even though they're multiple switches, allowing for a lot more redundancy, and if something goes down, you have a way to get in and monitor the switch and fix it. So that's what a stacking module is. Alright, so here's our fiber modules that go into our switches, and usually link them into the distribution layer with these. So we have these are called SFPs, which are the newer. This is what's going to happen with the newer switches. The ones we have in class are long, and most of them look like this, but they're square, right? But they're a lot longer than this. They're probably 3 times as wide as these SFPs. So these are called small form pluggable modules, and they come in different types, right? Like this one's a copper, 1000 base T. Whenever you see base T, that means Ethernet standard of copper. We have it just says optical SFP, but and then this one's BX, which is optical. But if we look down here, it shows us our fiber modules. So we have 100 FX, which is up to 2 kilometers. 100 base LX, which means 100 meg, right? Which these are old. Usually the fiber modules are gigs. 100 base LX, which is long haul fiber. LX means long haul. EX, I'm not sure what EX means, but these are 100 base, but 40 kilometers. And then ZX means super long haul. And so if we look down here, these are our gig modules. They're more common. SX means short haul. LX long haul, or sometimes they say LH long haul. ZX super long haul, and BX once again I'm not familiar with that. Base T copper wire. Then we also have 10 gig receivers, and now they have 40 gig receivers. But that's for another time. So, talked about those fiber modules. Now we have layer. I said layer 2 switches are layer 2, but we can actually have multi-layer switches. And what a multi-layer switch does is it works as a router, and so it can route and switch. And how a layer 3 switch works is, or any Cisco router, layer 2 used to be a lot faster than layer 3, and so a layer 2 device would just start fast forwarding. It has this ASICs chip that is based on which is just a semiconductor that its sole goal is to get frames to their destination as fast as possible. Cisco came up with this technology to make routing faster, where we use less of the CPU, and it's called Cisco Express Forwarding. And if a switch supports Cisco Express Forwarding, it is a layer 3 switch. And so how CEF works is it builds a forwarding information database, so what ports it's coming from or what IP addresses those are coming from, and then an adjacency table, which is its neighbors and who to forward to get to a certain network. So the router uses these three things: the routing table, the fib table, and the adjacency table. So after it's sent packets, the routing table knows through the fib table and through the adjacency table where to send packets that are coming for similar networks. And so our three types of layer 3 switching techniques. I really don't want to talk to you guys about this yet because it's confusing even when you're in CCNA2, but there's a switch virtual interface, and usually the switch virtual interface is just used to remote manage switches. Then a routed port is a switch that is working just like a router port, which we haven't talked about, so it doesn't make any sense. But basically what it is typically we can't put an IP address on a physical switch interface. That's why we make these SVIs. And so they're a virtual interface that we put an IP address on. But a router port, we actually put the physical IP address on it just like we would a router. And then a layer 3 ether channel is just where we would have a routed port, but we have two cables that virtualize into one, and that will not be something until CCNA 3. So this is all really big stuff, so if you don't understand it, read through here, but don't kill yourself on it because it's not that important. Just know usually the answer is SVI on the test, and just pull up this part of the chapter when you're doing the test. But anyways, when we program a switch into layer 3, if we want it to be layer 3, we say no switch port, and we also say IP routing, and that's the only two things. But once again, I don't want you guys setting up layer 3 switches yet. You don't actually do it till CCNA 3, and so I don't know why they're scaring you with it in CCNA 1, but hey, that's just how it goes. That was the Ethernet. I hope the layer 3 switching didn't confuse you too much. If you have any questions or comments, just hit the discussion boards or send me an email.